In this video, we are going to once more go through example 6, example 7 and example 8 which are applications of intermediate value theorem. So example 6 asks us to find and or show that there exists a number x naught such that x naught raised to 5 minus x naught is equal to 3. So when such a question is coming and we have to apply intermediate value theorem, we suppose f of x is equal to x raised to 5 minus x. Okay, we have to show that there exists a number x naught such that x naught raised to 5 minus x is equal to 3. That is, we have to show that f of x naught is equal to 3 because we have defined f of x like this. And note that this is a polynomial, and we already mentioned that all polynomial functions are continuous in the entire real line R. Okay, so keep that in mind. Now you just randomly find f of 0. When you find f of 0, you have 0 raised to 5 minus 0 is equal to 0, and similarly f of 1 will be 1 raised to 5 minus 1 is equal to 0. F of 2 is equal to 2 raised to 5 minus 2 is equal to 32 minus 2, which is equal to 30. And we understand that this f of 0, which is equal to 0, is strictly less than 3, which is strictly less than f of 2, which is equal to 30. Since f is continuous on the entire real line R, it is continuous on any subset of R. So in particular, we can say that it is continuous on closed interval 0, 2. We took the values 0 and 2 from here, okay. The 0 sitting here and the 2 sitting here. Okay, so f is continuous on closed interval 0, 2 subset of R. Now we have all the hypothesis of intermediate value theorem, which says that f is continuous on closed interval 0, 2, and that we have a number 3 such that f of 0 is strictly less than 3, strictly less than f of 2. That means there exists an x naught belongs to open interval 0, 2 such that f of x naught is equal to 3, and that will prove our example 6. And to see example 7, which uses method of bisection, and we need calculators for this, we have to find a solution for the same equation x raised to 5 minus x is equal to 3 in open interval 0, 2 with an accuracy of 0.1 by dividing the intervals repeatedly into half. So already we said that the equation x raised to 5 minus x is equal to 3 has a solution in in open interval 0, 2. That was example 6, right? There exists an x naught element of open interval 0, 2 such that f of x naught is x naught raised to 5 minus x is equal to 3. Okay, so we know that there exists such a number x naught. We have to find the x naught by bisecting. Bisecting means dividing into 2 the intervals. So as a solution, already now we know that from example 6, there exists an x naught belongs to open level 0, 2 such that x naught raised to 5 minus x naught is equal to 3. Now we have to locate this x naught very precisely. So you already found out f of 0 is equal to 0, f of 1 is equal to 0, f of 2 is equal to 30, and we used f of 0 strictly less than 3, strictly less than f of 2 earlier. We can even use f of 1 because f of 1 and f of 0 both are zeros, right? So f of 1 is strictly less than 3, strictly less than f of 2 because f of 1 is 0 and f of 2 is equal to 30. Now since as earlier said, the function is continuous in open interval 1, 2, and by intermediate value theorem we can say that there exists an x naught belongs to open interval 1, 2 such that f of x naught is equal to 3. So here there is an additional information. F is continuous in closed interval 1, 2 because it is a polynomial function, it is continuous everywhere. So using this fact and this fact, we can use the intermediate value theorem IVT to talk about the existence of x naught in open interval 1 2. Now we have to bisect 1 2. How to bisect? Divide into 2. How to find the midpoint? 2 minus 1 divided by 2. That is right. How to find the midpoint? Uh, you have 2 minus 1 by 2 is equal to 1 by 2 is equal to 0.5. So the midpoint you can calculate by 1 plus this 0.5. So you get it to be 1.5. So that's the midpoint. You form two subintervals by the bisection. That is, first subinterval is closed interval 1 1.5 and closed interval 1.52. Now find f of 1, f of 1.5, f of 2. F of 1 is 0, we know. F of 1.5, you use your calculator, scientific calculator to find it. 1.5 the whole raised to 4 whole raised to 5 minus 1.5, you get it approximately to be 6.09. F of 2 is 30. So you know that our 3 will be lying inside this 0 and 6.09, right? It will not lie in between f of 1.5 and f of 2. So it will lie in f of 1 strictly less than 3, strictly less than 1.5. So in order to use IVT, you have the additional information that f is definitely continuous on closed interval 1, 1.5. And with this information, you can apply IVT to get the existence of an x naught in open interval 1, 1.5 such that f of x naught is equal to 3. Now we are going to bisect this closed interval 1, 1.5. How to find the midpoint? 1.5 minus 1 divided by 2, that will be 0.5 by 2, which is equal to 0.25. Then add it with 1, 1 plus 0.25, that is equal to 1.25 will be the midpoint. So the two subintervals will be after the bisection closed interval 1 comma 1.25 and closed interval 1.25 comma 1.5. Now find f of 1. You know f of 1 is equal to 0. Here you have raised to 5. F of 1.25, you get that to be approximately equal to 1.80. You have to use a calculator and find the exact value, okay. And also f of 1.5 will be approximately 6.09. So our value 3 will lie in between f of 1.25 and f of 1.5. Okay, so in order to use IVT, you just have the additional information that f is continuous on closed level 1.25 comma 1.5, and this statement you can use the IVT intermediate value theorem to say that their exists and x naught belongs to open interval 1.25 comma 1.5 such that f of x naught is equal to 3. Now you are going to bisect closed level 1.25 comma 1.5 into 2. So for that, to find the midpoint, 1.5 minus 1.25, you get that to be equal to 0.25, right, divided by 2. So that will be 0.1, then 2, right, 5. So you add it with 0.125. You get 1.375 to be the midpoint. So when you bisect, you get that to be the two subintervals, closed level 1.25 and 1.375, and closed level 1.375 and 1.5. Then find f of 1.25, which is approximately 1.80, f of 1.375, which is approximately 3.54, f of 1.4, which is approximately 6.9, And you can understand that this f of 1.25 is strictly less than 3, strictly less than f of 1.375, and the information that f is continuous on closed level 1.25 comma 1.375. Use IVT, you get the existence of an x naught belongs to open interval 1.25 comma 1.375 such that f of x naught is equal to 3. So approximately you get x naught is equal to 1.3. Now example 8, you are given f is continuous on closed level 03, and f has no roots in closed level 03. That will mean f of x not equal to 0 for every x belongs to closed level 03, and also given f of 0 is equal to 1. We have to prove that f of x is strictly greater than 0 for every x belongs to closed level 03. So suppose B belongs to open interval 0, closed interval 3, that is B is lying in between, strictly lying in between 0 and it is less than 3 or equal to 3. Now consider closed interval 0B, and since F is continuous on closed interval 03, F is obviously continuous on closed interval 0B because it is a subset of closed interval 03. Given f of 0 is equal to 1, which is strictly greater than 0. Okay. And also note that f of b is not equal to 0, since f of x is not equal to 0 for every x belongs to closed interval 03, and b is happening to be inside uh, closed interval 03. So f of b is not equal to 0. So the possibilities for f of b will be either f of b is strictly greater less than 0 or f of b is strictly greater than 0. What should we prove? We need to prove that f of x is strictly greater than 0, so that we have to say that this will not happen. So suppose if not, suppose this f of b is strictly greater than 0. If we assume like that, we have to show that there will be a contradiction. Then we can conclude that f of b will be always strictly greater than 0. So if f of b is strictly less than 0, that will imply the function will intersect the x-axis. See, as an example, you know that f of 0 is equal to 1 from the hypothesis. Okay, and we have assumed that if this is b, a value in between 0 and 3, and f of b is strictly less than 0, we are assuming like that, and we know that a function is continuous. So definitely this function will have to meet at some point on this x-axis. That means if that line is called C is equal to 0, there will be an intersection like that. That means there is some point x naught such that f of x naught is equal to 0. Then this x naught is happening in between the 0 and b. And that is a contradiction because no value in between 0 and 3 can take 0. That means there are already in the hypothesis we are given that there are no roots for this function in between 0 and 3. So you have a contradiction here. This is a sign we use usually for contradiction. So it is not possible. That means the only possibility, this case is not possible. So the case 2 is the only possibility, that is f of b is strictly greater than 0. So what is b? From where this b is varying, b will come from open interval 0, 3, right? And already we are given that f of 0 is equal to 1, which is strictly greater than 0. So in general, we can write f of x is strictly greater than 0 for every x belongs to closed interval 0, 3. From both of these, you can conclude like this. So that is what we have to prove in example 8. So if you had any clarifications in this example, you can refer to this video and clarify your doubts. So thank you.